This evening we're going to explore another application of the logarithm in exponential growth and decay. Specifically, we're going to look at a different base. Last time we used a base of e for our population growth example. Well, in nuclear reactors, a lot of things will describe logarithmic behavior. Specifically, we're going to define our growth rate of power, so our rate of change of power increase or decrease as a logarithmic function. We're going to define it as the units are decades per minute. If we read DPM, that equates to a change in power by a factor of 10. 1 decade per minute equals a change in power by a factor of 10. Okay. So for a 1 decade per minute startup rate, if we were at time 0, the power was 1%. If we had a 1 decade per minute startup rate, at time equals 1 minute, it would be 10%. At 2 minutes, it would be 100%, and so on. If we had a 2 decade per minute startup rate, at time 0, we would be at 1%. At time 1, we would be at 100%. And then at time equals 2 minutes, we would actually be at 10,000%. Okay? Now this seems kind of like a large amount of change very quickly. Well, 1 decade per minute, we routinely change power by this much on a regular basis. However, during reactor startups, whenever we're taking the reactor from a very cold, very shut down condition to running at full power, we can actually change power by up to 5 decades per minute. So 5 decades per minute during reactor startup. So that's a factor of 10 to the 5th, or a factor of 100,000 times every minute that we're actually increasing power. So this is why we actually have to define it, our startup rate, as a function of a logarithm. Okay? So, how do we actually define the decades per minute? If you recall, last time, your basic growth rate example was given by p to the t equals p at time 0 e to the lambda t. Note that this is base e. Base e. For a different change of base or a different exponent, we're going to use a different number for this, but it's still, basic form is still going to be the same. So for our example, we're going to use p to the t equals p at time 0, but instead of e, we're going to use 10 as a base to the lambda t. Now, what is this lambda? Well, that lambda is actually your startup rate, or your decades per minute. Okay? So the function we need to know is p to the t equals p naught 10 to the startup rate t, and SUR would be the abbreviation for startup rate. So let's look at an actual negative example here. Let's say we're operating at 100% power. Cruise along and you're at 100% power. Let's say you are a reactor operator, you're going to have control of your control rods, and you insert your control rods to slow down the amount of fissions that happen in the core. 1 minute later, you're at 50%. What's your startup rate? Okay. Well, just like before, we're going to use the equation and use our base logarithms to bring down the exponents and solve for it. So let's go ahead and start doing that. So if you recall, p to the t equals p naught 10 to the startup rate times your time. Well, 1 minute later, so t is equal to 1 minute, we're going to have 50% equals 100% times 10 to the startup rate. And this time, t equals 1 minute, so that's times t startup rate equals 1. So therefore, that's going to go away, and you're just going to have 10 to the startup rate. So what's 50%? I'm going to divide each side by 100%. That's going to give 1/2 equals 10 to the startup rate. Now before we took the natural log of both sides. Since this is base 10, we're going to take the log base 10, or simply log, of both sides. So our log of 1/2 is going to equal our log of 10 to the startup rate, which is just going to equal our startup rate. Okay, so our startup rate is equal to log of 1/2. So therefore, plug that number into your calculator. You're going to get startup rate, in this case, is going to be equal to negative 0.301. If you did the example in reverse and went from 50% to 100% power, you would see that your startup rate would be positive 0.301. This is important to know. Therefore, you know that whenever you're operating and changing by a factor of 2, roughly 50% is equal to 3 on your logarithmic base scale.